Hey guys, welcome back to week 5 of my series where I'm learning ML through an optimization perspective. So this week I covered section 2.6 on dual cones and generalized inequalities from the Boyd book. I also reviewed some material from the previous sections. So in total I spent about 13 hours studying this week. So this week was really interesting because dual cones connect back to a lot of linear algebra concepts I learned before, especially around inner products and orthogonality. So the main thing I learned was how dual cones give us a dual perspective on generalized inequalities. So instead of checking if something belongs to a cone directly, we can check it using inner products with the dual cone. So this kind of creates a beautiful duality where every cone has a partner cone, and understanding one helps you understand the other. So then I connected these general concepts with the specific concepts from linear programming, which is a class I took prior to this what I'm doing now. I explored how the primal and dual problem described by linear programming is a special case of this much more general structure encoded by these dual cones. So I really had a blast this week, as the last section from this chapter 2 helped me tie up all the loose ends of how we actually connect what I already know in linear programming to the more general and elegant mathematical framework. And I'm going to show you guys what I mean later. So on that note, I also got to see Farkas Lemma, which turns out to be just the separating hyperplane theorem applied to cones. So that was a really cool moment. So despite all this, I was pretty busy with work this week, and I anticipate I'll be busy next week too. So I'm going to travel to Vietnam in about a week from where I'm currently staying in Tokyo. Okay, before introducing dual cones, let's start with some motivation. So remember from last week that we defined generalized inequalities using proper cones. We said that if x is less than y under the generalized inequality, so under the set k, that means that y minus x is in k for some proper cone k. Remember that if k was the real numbers, then we just recover our regular and familiar um, inequalities. But here's a natural question. How do we actually characterize membership in a cone K? So what's another way to think about what it means for a vector to belong in K? So that's where the dual cones come in. The dual cone gives us an alternative perspective using inner products. It's a fundamentally different way of thinking about cones that reveals deep connections in optimization theory. So the dual cone seen here, K star, is defined as the set of all vectors y such that the inner product y transpose x must be non-negative for all x in the cone K. Okay, so what does this mean? Well, let's draw some pictures. So imagine K is some cone in two-dimensional space. So some vector y is in the dual cone K star if when you take the inner product with any vector x from K, you get a non-negative result. So on screen in the middle here, we can see the different vectors in K, so x1, x2, x3, and you see some y vector pointing in a similar direction. So we can see, just visually speaking, that the dot product between this y and all the vectors, so x1, x2, x3, and all the rest of them in K must be positive. This is because they're not and they don't form an obtuse angle with any vector. So geometrically, this means that y makes an angle of at most 90 degrees with every vector in K. So the dual cone consists of all vectors that point in a generally similar direction in K. So let's build more intuition with a simple example. So let's consider when K is a very, very narrow cone in R2, almost like a ray. So we ask, what does a dual cone look like? Well, We need all vectors y where y transpose x is greater than 0 for every x in this narrow cone. But since k is narrow, y has a lot of freedom. It just needs to make an angle less than 90 degrees with every vector in the cone. This means that the resulting k star, or the dual cone, is very wide. So now let's go the other way. Consider a very large cone K in R2. So this is about 160 degrees opening. So what is K star, or the dual cone? Well, again, we want to find the cone or find vectors y such that it makes um, positive uh, y transpose x greater than 0 for all such vectors in K. So since there's a lot of different vectors pointing in different directions in K, this is a much more restrictive condition. So that means that K star ends up being a very narrow cone. So that means that there's an inverse relationship. When K is large, that means that K star is small and vice versa. So just as an example, this wide K might have a K star that looks something like this. It's very narrow because every vector in K star must be within 90 degrees of all the vectors of K. So these ideas seem rather abstract, but they have deep implications in optimization theory. And we will see exactly that when we connect these ideas to linear programming. So let's look at another example. So let's say that our cone K is simply the set of all positive vectors. So what is the dual cone of the positive orthant? So we need to find all vectors y such that y transpose x is greater than 0 for all x in this positive orthant. So the key insight is when we choose x to just have one component equal to 1 and all the others equal to 0, then x is the ith standard basis vector. So that means in the ith position is 1 and everything else is 0. So what this means is that if you multiply y transpose with x, which in this case is the ith standard basis vector, you simply get the component of y corresponding to the ith standard basis vector, so that's just yi. And since we require y transpose x greater than 0, this means that yi must also be greater than 0 for all I. And wait a second, this is exactly the definition of y, the vector, being in the positive orthant as well. So for k being the positive orthant, we can construct the dual cone by all the vectors also in the positive orthant. This means that the dual of the positive orthant is itself, which is the positive orthant. So we call this property self-dual. So this makes sense from our earlier intuition. The positive orthant in R2 is a 90-degree cone, so therefore its dual must also be a 90-degree cone by the inverse relationship we saw earlier. Now let's explore something that's really cool, the connection between these dual cones and what we call dual norms. So let's define what we mean by dual norm. So given some norm, its dual norm, which is a norm star, is defined as, so in other words, the dual norm of y is the maximum value of y transpose x over all x in the unit ball of the original norm. So here's a diagram to represent that idea. So we can see here for L2, the unit ball is simply a circle. So this represents the maximum value of y transpose x over all x in the norm ball. So this is a nice geometric interpretation. The dual norm measures how much y can stretch when applied as a linear function to unit vectors. recall the norm cone we studied earlier, K associated with the norm. So this looks like a cone in Rn+1, so like in ice cream cone shape. So here's really the beautiful result. The dual of the norm cone is the norm cone of the dual norm. So my claim is that the dual norm, K star, is simply just another norm cone, but using the dual norm instead of the regular norm. So let me show you why. So we need a y and an s such that ys transpose times xt is greater than or equal to 0. And so if you do the multiplication out, you get this expression here. And this is for all x less than or equal to t. So the worst case of this expression is when y transpose x is as negative as possible, right? So by the definition of a dual norm, we have y transpose x is greater than or equal to negative of the dual norm y times the norm of x. So for this to be non-negative when the norm of x is less than t, we need the negative of the dual norm of y times t plus st must be greater than or equal to 0. So that implies that the dual norm of y must be less than or equal to s. So this is exactly the norm cone for the dual norm. So let's look at some examples of different norms. So for example, we'll look at the L2 norm, the L1, and the L infinity norm for these norm cones. So for the L2 norm, of course, we have these familiar results. The L2 norm of x is simply just the distance using Pythagorean theorem. Okay, so what is the dual norm? So we need to find what this expression is equal to, which is the supremum of y transpose x such that the L2 of x is less than or equal to 1. But we know that y transpose x is less than or equal to the norms of y and x multiplied together by the Cauchy-Schwarz inequality. But when the norm of x is less than or equal to 1, that gives us y transpose x is less than or equal to just the norm of y. So the supremum, or if you want to think about it as the maximum, is achieved when x points in the same direction as y. So specifically when x is equal to y over the norm of y. So plugging in x into y transpose x, we have y transpose y, which of course is the norm squared over the norm of y. So if you cancel out one exponent, you're just left with the norm of y. And so we've shown that the dual norm of y under an L2 norm is equal to the L2 norm. So what this means is that the L2 norm is self-dual. So this also means that the L2 norm cone is also a self-dual as well. So this is why the ice cream cone is self-dual. Okay, so that's L2. Let's look at L1 next. So remember the L1 norm of x is simply just the sum of all the absolute values of the components of x. And so the dual norm is simply, we want to find the maximum or the supremum of y transpose x subject to this L1 norm constraint. So let's figure out what this dual norm is equal to. So to find the maximum y transpose x, we write out this small optimization problem here. So let's think about this problem a little bit further. So remember, we can write out the expanded form of this dot product. So the dot product, remember, is just the component-wise multiplication. So the key insight here is to maximize y transpose x, we should put all of our budget, so to speak, of one component, where yi is the largest.
Specifically, if yj is the largest component in absolute value, we should set xj equal to the sign of yj, and all the other xi's equals 0. So notice that when only one component of x is 1 and the others are 0, then this condition holds. And when y has a maximum component, then we want to multiply this by the biggest number we can, which is 1, to maximize the dot product. So what this means is that when we take the dot product now, y transpose x, where x is simply just the sign of yj with everything else being 0, um, then the dot product is equal to the maximum of yi, but the maximum of yi is simply just the infinity norm. So the dual norm of L1 is the infinity norm. So by symmetry, let's verify that the dual of the infinity norm is L1. So again, we want to find what the supremum of y transpose x subject to this norm constraint, what that actually is equal to. Okay, so let's think about it more closely. So the infinity norm of x is simply just the biggest absolute value of the component. This means that we don't really care about what is happening to the other components. We only care for this constraint that the biggest component is less than or equal to 1. So that means we can choose the value of each component of x independently of one another, as long as the biggest one is less than or equal to 1. So we should notice that this assignment satisfies the constraint, and what it does is it converts y transpose x into a simple addition of absolute value of the components of y. For example, if y was a vector -1, 3, then x would therefore be -1 and 1. So when you do a dot product, you would have -1 times -3, which is 3, and 1 times 1, which is 1, which gives you the most you get out of that dot product, which is 4. But the simple addition of absolute value of y is simply just the L1 norm of y. So we've shown that the dual norm of y under the L infinity norm is simply just the L1 norm of y. So the dual norm of L infinity is L1. So they're dual to each other. So just to summarize what we just did, here's a picture of all the different norms we explored. So first we explored the L2, which is the Euclidean distance. And remember, all these norms are less than or equal to 1. And we saw that the L2 norm is self-dual. For L1, that's the sum of all the absolute values. And oh, by the way, these pictures are in two-dimensional space, right? So you only have x1 and x2. So if x1 plus x2 is less than or equal to 1, then you get this diamond shape here. We show that the L1 is dual to L infinity, and L infinity is dual to L1. And of course, we get the square shape for L infinity because we can choose each component of x independently of one another. That's why we go from the full -1, -1 to 1, 1. Okay, so what about positive semi-definite cones? So notice we're not dealing with vectors anymore, and so the dot product is going to be defined a little bit differently. But we basically need to find all matrices y, such that the dot product defined under matrices of y and x must be greater than or equal to 0 for all x that are positive semi-definite matrices. So here we define the dot product between y and x as the trace of the y transpose x. So just a reminder from linear algebra, a symmetric matrix X is positively semi-definite if and only if, for some vector z, z transpose x times z is greater than or equal to 0 for all vectors z. Now if y is positive semi-definite and x is positive semi-definite, then the transpose of yx is greater than or equal to 0. That's my claim. To see y, we can write um, the trace of yx as the trace of the following expression using properties of the trace. And since this inner expression is positive semi-definite, its trace must be non-negative. Conversely, if the trace of y times x is greater than or equal to 0 for all positive semi-definite x, then y must be positive semi-definite. To see this, we choose x to be z times z transpose, and we use the property of the trace to move the z on this side. And of course, that implies that, well, since y is positive semi-definite, that means that this must be greater than or equal to 0 as well. So all this to say is that the set of symmetric positive semi-definite cones is also self-dual. Okay, so why is this dual cone perspective thing useful? So it's about having two complementary ways to think about the same object. So the first way we learned was that X simply is just belonging into the set K. So this is kind of a constructive view. We construct the set K by all these X's that belong into it. But we can also look at the dual characterization, which is that the set K is all X's such that lambda transpose X is greater than or equal to 0 for all lambda in the dual cone K star. So this is the functional view. So the dual perspective lets us to test membership using linear functions, or in other words, inner products, rather than checking geometric conditions. So this is incredibly powerful in optimization theory because it converts geometric questions into algebraic ones, and it can reveal hidden structure. For example, self-duality tells us that a cone has special symmetry, and it connects to later topics in optimization, which we'll see in a few weeks, like dual theory, which, as you can imagine, has deep connections to these topics. So just concretely, when we found that the L1 norm and the L infinity are dual to each other, this immediately tells us that optimization problems involving L1 regularization have a dual form involving L infinity constraints, and vice versa. So the geometry of one norm is reflected in the algebra of its dual. Okay, so now here's where the dual cone gives us a powerful recharacterization. So remember our generalized inequality, x is less than or equal to y under the set K. So that means that y minus x is also in the set K. So using the dual cone, we get an equivalent characterization. So the characterization is that x is less than or equal to y is the same thing as for some lambda in the dual cone K star, lambda transpose x is less than or equal to lambda transpose y. And so if we move the lambda x on the right side and factor out a lambda transpose, we get the lambda transpose times the difference, or y minus x, is greater than or equal to 0. So this is huge. It's saying that checking the generalized inequality is equivalent to checking ordinary real inequalities, one for each lambda in the dual cone. So this dual characterization is foundational to duality theory and convex optimization. So we'll see that every generalized inequality in the primal can be tested using elements in the dual cone. So let's see how these dual cones naturally lead to duality in optimization. I want to show you how dual problem arises from the dual cone perspective. So let's start with a general optimization problem. Remember, in linear programming, we simply want to minimize the dot product between some cost factor and x. So we just want to pick x such that this value is maximized. But of course we can't make this to infinity because we have some constraint that ax is less than or equal to b. In this case we use the generalized inequality for some set k. And we also say that x must be in some set c. Usually c is some convex set. Usually x is just greater than or equal to 0. So for simplicity, let's just assume that c is equal to k prime for some proper cone k. So our problem now is as follows. Okay, great. So all this stuff should be familiar, and we're just using linear programming concepts with the addition of the generalized inequality. So the question is, what should the dual problem be? So the dual problem turns out to be as follows. So instead of minimizing c transpose x, we want to maximize b transpose y, where b is this vector here. And subject to a transpose y is less than or equal to k prime, which again is the set that x is from, and that's less than or equal to c. And y must be in the dual cone k star. And of course we can rewrite this as follows. So notice the symmetry here. The primal has a constraint. So the primal is the top one. The primal has a constraint cone k, and a variable cone k prime. But the dual has a constraint cone k prime and the variable cone k star. So what this means is that the variables y are called the dual variables, and they naturally live in the dual cone, so k star. So at this point I've just been showing you some results, but let's see why it must be in the dual cone. Well, it turns out the ultimate reason why this is the case is that we must have weak duality. Is that the shadow prices of the dual problem, so b transpose y, must be less than or equal to the objective cost or the objective function of the primal problem. So in other words, by this construction, the dual, we require that the dual must be a lower bound for the primal. To see why that weak duality implies that y is in the dual cone, notice that if c minus a transpose y is in k, that means that in the dual cone, anything in k, in this case k prime, must be a dot product with x that's positive. So by properties of dual cones, we must have c minus a transpose x times y transpose times x is greater than or equal to 0. So if you do some algebra and rearrange a little bit, then we recover our weak duality as desired. So this is Tyler. Just a little bit later, I want to make a clarification. The reason this works is because I kind of assume that k prime and k is the same. So as long as that's true, the same argument applies. So usually for linear programming, our set k is simply just the set of all positive vectors, right? So that means is that the b minus ax is in the set of positive vectors, and each row is a constraint, and that must be greater than or equal to 0. And remember that the set of positive vectors is self-dual. So that means that the dual cone is also a set of positive vectors as well, and so the dual variables must also live in the same space as the primal variables. So now I'd like to show you one of the most beautiful results in optimization theory, which is Farkas Lemma. So I learned about Farkas Lemma in my class, and we learned it under the context of linear programming. But I just learned how it connects to the dual cones we just talked about. Turns out that Farkas Lemma is simply just a separating hyperplane theorem just applied to cones. Okay, so what is Farkas Lemma? Farkas Lemma is stated as here. So Farkas Lemma states that there exists x greater than or equals 0 such that ax equals b, or, and not both, there exists y such that A transpose y is greater than or equals 0 and B transpose y is less than or equal to 0. So I want to answer two questions. Why is this interesting, and what does this have to do with separating hyperplanes? So let's think about it geometrically for a second. So the columns of A are the vectors a1 through an, and these vectors live in our M space. Equation ax equals b with x is greater than or equal to 0, as can we write b as a non-negative combination of the columns of A? And so we can see b here. So in other words, is b in the cone generated by the columns of A? So let's see be this set of vectors which are the columns generated by the matrix A. And so we simply ask, is B in this set as well? So there's two worlds. Either B is in the set C or B is not in the set C. We claim that if B is outside the set C, then we can separate C and B with a hyperplane. So let me remind you of the separating hyperplane theorem from section 2.5. So the theorem just says that if C and D are non-empty disjoint convex sets, so it means the intersection is empty, then there exists a separating hyperplane that goes between them. So meaning that there's an A that equals 0 and beta such that A transpose X is less equal to beta for all X and C, and A transpose X is greater than equal to beta for all X and D. So we can say that the hyperplane X such that A transpose X is equal to beta is the hyperplane that separates C and D. So let's apply this to our problem. So we can let our C remain the same. So this is the set of AX such that X is positive. And then we can let D be the single point B. And so if C intersect D is empty, so they don't intersect, that means we can find a hyperplane that separates C and D. So just it immediately follows that by the separating hyperplane theorem, there exists an A not equal to 0 and alpha such that A transpose X is less than equal to alpha for all X and C, and A transpose B is greater than alpha, provided that C and D have an empty intersection. So here's the key idea. C is a cone, which means it contains the origin. So that means that X can be 0, right? But since 0 is in C, we have A transpose 0 is less than equal to alpha, which implies alpha must be greater than equal to 0. Second, for any x in C and any t greater than equal to 0, we have t times x must also be in C. This is just a property of a cone. So we can replace x with t times x for some positive t, and we have that t times A transpose x is less than equal to alpha. So consider when A transpose x, so inside the parentheses, is greater than 0 for some x and c. Then as t approaches infinity, we have this expression approaching infinity as well, since t is positive. But we can choose t big enough such that this inequality is violated. Therefore, we must have A transpose x is less than or equal to 0 for all x and c. So combined with alpha is greater than or equal to 0, and A transpose B is greater than or equal to alpha, we have the following chain of inequalities. So we see there here that A transpose X is less than or equal to 0, so that's just our expression here, and 0 is less than or equal to alpha, which we find here, and alpha is less than or equal to A transpose B, which of course is here. Okay, what this result means is that, indeed, if it's the case that C and D does have no intersection, so that the second condition of the Farkas lemma is true, then we can find a separating hyperplane such that y transpose x is greater than 0 for all x and c, and y transpose b is less than 0. Okay, now using this result, we know that y transpose x is greater than 0 for all x and c. Remember, c was constructed by all these vectors ax, so we can replace x with ax. And we see that y transpose ax is greater than or equal to 0 for all x is greater than or equal to 0. So we can just simply rewrite that with the property of transpose. And for this to hold for all x is greater than 0, we should test it with x being the ith standard basis vector, so e of I. So we have this inequality here, which is the ith row of A transpose Y is greater than or equal to 0. So notice this must hold true for all I. That means we have the generalized inequality A transpose Y must also be greater than or equal to 0. Combined with the fact that B transpose Y is less than 0, we recover exactly condition 2 of Farkas lemma. So Farkas lemma is just a separating hyperplane theorem applied to cone C and to the point B. So we can also see Farkas lemma through the dual cone perspective. So remember the condition y transpose times ax greater than or equal to 0 for all x is greater than 0 means that y is in the dual cone of C. And we have shown that the dual cone of C is simply just a set of vectors y such that A transpose y is greater than or equal to 0. So what statement 2 of Farkas lemma is really saying is that there exists some y in the dual cone of C star, such that y transpose B is less than or equal to 0. So the hyperplane y transpose x equals 0 separates B from cone C, with y being the normal vector to the hyperplane. So Farkas lemma really has three uses or perspectives. So the first one being the separating hyperplane we first talked about. So the theorem talks about sets C and D, but if we introduce our cone C as we did here in our point B, which is our set D, then Farkas lemma is just the separating hyperplane theorem for these sets. But we also know that if y is in the dual cone of C with y transpose B is less than 0, that also proves that B is not in C. Lastly, this provides us a way to prove a negative, which is that we have a certificate of infeasibility for linear systems. So in linear systems, we want to find some sort of solution to ax equals b. But if B is not in the column space of A, we now have a way to see, or at least to prove, that there is no X such to make that linear system satisfied.
So that wraps up section 2.6 on dual cones. So this really was a rich section which connects norm duality. So we saw how L1 is a dual of L infinity and vice versa, and we saw L2 is a dual of each other, or self-dual. We connected to linear programming and optimization duality, and we saw Farkas Lemma as separate hyperplanes for cones. Lastly, we also saw supporting hyperplanes and dual characterizations. So the dual cone perspective is fundamental because it gives us two equivalent ways to think about order structures: the direct geometric view and the functional view. Each perspective reveals different structure about the optimization that we were interested in. So what really amazed me was how everything connected together. The dual cone naturally leads to dual problems in optimization. Farkas lemma is just the separated hyperplane theorem, and the optimal points are characterized by supporting hyperplanes. So, it all fits together really elegantly. So there's actually more that I learned, which I wasn't able to cover. This was about minimum and minimal elements. So under regular inequalities, we have a way to talk about minimum elements of a set pretty naturally. However, these concepts are slightly nuanced for generalized inequalities. So this week I learned about their dual construction. But since I'm out of time this week, I think I'll leave this topic for next week. Speaking of which, for next week, I'm planning to do a bunch of problems. I won't cover any new material, so I won't jump to chapter 3 next week. So maybe I'll walk you through some harder problems or two as I work through them, and then probably also cover the minimum elements I just mentioned. So anyways, that's about it for this week. So thanks for watching, and I'll see you next week.